The word force is used quite a bit these days. A government may threaten the use of force on another nation. A child may scream in protest at being forced to clean their room. But even though we may not automatically think there's any kind of scientific connection to our everyday use of the word, these real-life examples are very helpful in helping us understand the forces that are unseeable, but always at work. According to its definition, force is defined as the push or pull upon an object resulting from its interaction with another object. While the forces at play in our world might not be as obvious as one nation retaliating against another when pushed, they are still essential for every single aspect of our lives. Without the four fundamental forces of nature, the universe as we know it could simply not exist. But what are these forces, and how are they responsible for everyday life? Let's begin with something that's probably already familiar to you, the force of gravity. Before gravity was completely understood, it was thought that planets and stars were purely a creation of a god or some unknown phenomenon, and their movements couldn't fully be explained. It wasn't until we got to Galileo that the world really began to question why objects move the way they do. Galileo was the first person to observe that objects thrown from the same height seemed to pick up speed at the same rate. He also correctly observed that all bodies fall with the same acceleration, as long as air resistance and buoyancy aren't a factor. While he was on the right track, it wasn't until a few decades after Galileo's death that the theory of gravity was officially presented by Isaac Newton. As the story goes, just a single apple changed the course of science forever. Maybe. Newton correctly concluded that gravity was a force that existed between all objects with mass. It pulls objects towards each other, and the more massive the object, the greater the pull. That's exactly why when we jump into the air, we don't just leave the planet. The Earth is huge. Its gravitational pull is way too strong, keeping us all squarely on the ground. This is good because, well, we aren't flying away. But when it comes to us actually wanting to leave the planet, well, it just sucks. Literally, gravity is the main thing holding us back from easily accessing space. If gravity was just a bit more forgiving, well, we might already be living on the moon or Mars. Except, we really wouldn't. We need gravity. Gravity is what keeps the planets orbiting the sun, our moon in orbit around us. But it isn't exactly what's holding our galaxy together. There, we venture to dark matter and dark energy. Those are separate videos, but just note, without gravity, the planets would have wandered off long ago. The sun wouldn't have heated the Earth, and none of us would be living to watch this video. Gravity is still an important area of study, and more discoveries have been made since Newton. Most notably, Einstein's discovery that the force of gravity works not only on mass, but on light as well. Of course, this isn't visible to the naked eye, but it is measurable, and this discovery added valuable knowledge to our understanding of gravity and how it works. General and special relativity, well, we'll talk about those another time. But as important as it is, gravity really isn't that strong. Next to gravity, something called the weak force might not sound so impressive, but it's a force that is even more powerful than gravity, albeit only at very short distances, 0.1% of the diameter of a proton. While this distance is obviously not perceptible to humans, it more than does the job. The weak force is an interaction that happens exclusively between subatomic particles. When the weak force is at play, they can exchange three different force carriers, known as bosons. These are essentially tiny little bundles of energy. This exchange of positive and negative W and Z bosons is what allows quarks, the particles that make up neutrons and protons, the ability to essentially change their flavor. This theory was proposed in 1933 by Enrico Fermi. He discovered that this happens when a nucleus finds itself with too many protons or too many neutrons, and so eventually one of them is turned into the other. In simple terms, the weak force can physically change one particle into a different particle. This process is known as beta decay. In one of the most common examples of the weak force, we can look at carbon-14. Because of the weak force, we know that carbon-14 changes into nitrogen-14, and because of this, we have been able to use radiocarbon dating to determine the timing of significant events throughout history. But while all of this work is important and certainly interesting, the most striking example of why the weak force is so crucial to us here on Earth and in the solar system in general is due to its role in nuclear fusion. While there are other forces at play, the weak force is ultimately what sets off the grand finale. It's what powers the sun by helping to convert millions of tons of hydrogen nuclei into helium every second, releasing extremely large amounts of energy that produces the very heat that keeps us alive each day. You wouldn't be wrong to think that the electromagnetic force sounds like two different things. In fact, for a long time they were believed to be two separate forces, until it was eventually discovered that they were both part of the same process. It serves to remind us that science is constantly evolving. Theories are made using the best research and facts, but there are never any finite endings in science. We work on the small details, building up research available to us until we can update it with additional information. As is true for most discoveries in science, there wasn't a big aha moment, but rather a gradual change of attitude over time. However, it was the Danish physicist Hans Christian Ørsted who officially discovered that there was a connection between electricity and magnetism. During a lecture, he noticed that a wire carrying an electric current seemed to shift the needle of a nearby compass, so much so that it ended up being perpendicular to the wire. This is something that most people would never notice, but it was this event that prompted him to realize that a straight wire with an electric current passing through it actually generates magnetic field lines that encircle the wire. All that from a compass. The reason this phenomenon happens, if you haven't already guessed it, is because electrically charged particles generate electric fields. This happens because positively charged protons push away other protons and attract negatively charged electrons, and the same thing happens in reverse. Because of this reaction, electric field lines spread out from these electric charges and push particles either to or away from the field lines, depending on whether they are positively or negatively charged. If it sounds confusing, I get it. But listen, the electric force is something that is always happening between charged particles, but for the magnetic force to come into play, there must be movement involved. It's hard to describe exactly how the electromagnetic force operates in every single function, but without the electromagnetic force, we wouldn't have the processes of tension, elasticity, and friction. It doesn't sound like much, but you wouldn't be able to put your kid's ugly macaroni art on the fridge because magnets wouldn't exist, and neither would tape. But one of the most important functions to come out of the electromagnetic force is the normal force, which is the action of two surfaces pushing against each other to keep them in place. That's why your mug of coffee can stay sitting on your desk instead of crashing through it due to the pull of gravity. It's almost like all of these forces are essential for everything we do in life, aren't they? Last, but certainly not least, we have the strong force, so named because, you guessed it, it is indeed the strongest force out of the four. As mentioned earlier, quarks are the building blocks for bigger particles, such as protons, neutrons, and electrons, which make up the atomic nucleus in the center of an atom, upon which everything in the universe is built. But what actually holds everything together? Why do atomic nuclei not simply separate and fly off in different directions? The answer is exactly this: the strong force. The strong force manages to override the electrostatic repulsion and holds the protons together in the nucleus, even though they technically repel each other. Not only that, but the strong force helps quarks bind together, which is how bigger particles known as hadrons, which include both protons and neutrons, are made. In 1935, a Japanese physicist by the name Hideki Yukawa determined that the strong force must be the result of particles now known as mesons, acting as force-carrying virtual particles. Just as with the case of the weak force, Yukawa also determined that the range of the strong force must be incredibly small, less than the diameter of an atomic nucleus. Today, it is known that the strong force operates on two different scales. On the larger scale, which is still tiny, the force indeed carried by mesons actually binds protons and neutrons together to form the nucleus of an atom. On the smaller scale, it's the exchange particles known as gluons that hold quarks together, which can then form neutrons, protons, and everything else that works together to ultimately create a hadron particle. There's a lot to it, and keeping track of what each of these particles do is kind of difficult. As already mentioned, the strong force is, well, strong. In comparison to the other forces, it's 1,000,000 times stronger than the weak force, 137 times stronger than electromagnetism, and unimaginably more powerful than gravity. If the strong force didn't exist, then there would be nothing to hold together the particles that make up everything on Earth. It's an essential piece of the puzzle. While it might be tempting to claim that one force is more important than the other, there's no world where that could be true. At least not one that we could ever live on. Like the cars that we drive or the computers that we use each day, each part has a unique function that makes up a whole. Lose one piece, and the whole thing can quickly fall apart. While there were a few key names I listed, the advancement of our understanding of the four forces of nature has been contributed to by many important figures throughout history, many of which did so without necessarily even realizing what it is they were observing. There were also those who felt confident that they were onto something, but weren't allowed to explore their ideas further. For example, Galileo supported heliocentrism, the idea that the sun was the center of our solar system, But his ideas were deemed so radical at the time that the Catholic Church labeled him a heretic and banned him from speaking on the idea, despite growing proof that he was correct. These things unfortunately still happen today. For years, scientists have been working to prove the existence of gravitons, the hypothetical elementary particle that mediates the force of gravity. While we have yet to prove its existence, that doesn't mean it isn't out there. Our discovery of these things, while extremely exciting, doesn't mean that much. As I said earlier, we're slowly building up our research. These particles, these forces of nature, well, they've always been there, and they always will be, whether we're conscious of them or not. It just makes me wonder, how much is out there just waiting to be found? And even deeper, what about the things that exist that will forever remain in the shadows, unbeknownst to us, as the millennia pass by? We've done pretty well so far, but just know, we aren't done yet.